Okay, we now have solutions for the wave functions. We take those wave functions, we substitute them back into the Schrödinger equation, and we'll determine the energy. We solve for the energy then. And the energy we find in the Schrödinger equation only depends on n. This was a sufficient explanation to explain the hydrogen atom spectrum at the time that it came out, and to the available resolution. Wow, it looked like the system had been solved. But those pesky spectroscopists, they keep getting better. Their resolution improved, and soon spectroscopists measured a difference in the n equals 2. They found that they're not exactly degenerate, so something more must be going on. And what's that? That's where the Dirac equation comes in. In the conventional Schrödinger equation, right, let's call that Hamiltonian H naught now, right? We just have the kinetic energy and the potential energy terms, and therefore we get this energy that depends just on the value of n, the principal quantum number. Dirac comes along then, and he uses a fully relativistic four-dimensional, right? He treats time as an equal coordinate to the three spatial coordinates. So it's a four-dimensional problem that he's going to solve. So he takes the Schrödinger equation, makes it fully relativistic. And what does he find? Well, we're not going to look at his exact treatment of it. Instead, we're going to look at it in this way. We'll introduce the idea of perturbation theory. Perturbation theory is take the main interactions in the system, solve that, right? And that we already have. That's the Schrödinger equation in 3D. And then add into it smaller terms into the Hamiltonian. And we can solve each one of these independently and just add on the energy then to that which we found for the zeroth order term, right? So the way we can treat the Dirac equation is in terms of this sort of perturbation theory. These should be small terms compared to that one there. This first term, h sub n, that's the mass velocity term. Oh yeah, in relativity, E equals mc squared, right? There's a relativistic correction to the momentum of the electron. So we understand that. So especially when the electron gets very close to the nucleus, its velocity is so high, right? It starts getting to be an appreciable fraction of the speed of light. Therefore, you get that relativistic correction to the electron's momentum. The second term is the Darwin term. No one really understands that very well, so we'll just skip over it. It's not huge. It's in there. It's good. It doesn't introduce any new structure either, so we don't have to worry about that one so much. The really important one is this final term here, this spin orbit term. The electron has an intrinsic magnetic moment that's related to its spin, and that spin is an angular momentum that can couple to the orbital angular momentum through this dot product here of spin times the orbital angular momentum, right? And that is the term that's really key for understanding what's going on here. Okay, so in the simple Schrödinger equation, energy only depends on n, so all the n equals 2 levels have the same energy. They're all degenerate. But when you do the fully relativistic treatment, boom, spin falls out naturally in that case, right? And we get these four quantum numbers, n, l, m sub l, and s, and they all play a role in determining and defining the energy of the system, because from the Dirac equation, we get this spin-orbit interaction, and that lifts the degeneracy here. You see, there's a small splitting, about 4/10 of an inverse centimeter. That lifting of the degeneracy is caused by these two different values of J, J being the total angular momentum, L plus S. Also, this explains the Pauli exclusion principle, because without just bolting it on, but from a priori, right, it comes right out of it. The spin can either be up or down, and therefore our full wave function must include not only the radial part, not only the angular, the spherical harmonics, but we need a spin function in here as well to say whether the spin is up or down for the electron, and we can only put two electrons in an orbital right? We now have a spin orbital, the spatial part and the spin part here. Everything seems great. Nobel Prizes getting thrown out all over the place. Heisenberg picks up one. Schrödinger and Dirac get it together. Pauli gets it as well for his spin and all of that. Everyone's patting themselves on the back. It seems like a great time to be a physicist. They've just figured out everything. And then the spectroscopy gets better. In 1947, Lamb and Rutherford measure the Lamb shift. 1955, Lamb gets the Nobel Prize for having found that, and this necessitated the introduction of quantum electrodynamics, QED. That would successfully be done by Feynman, Schwinger, and Tomonaga. And in 1965, Feynman, Schwinger, and Tomonaga would get the Nobel Prize for their development of quantum electrodynamics. What they found is that not only does spin orbit splitting split out the J 3 halves from the J 1 half term, but there's a small splitting between these two J equals 1 half terms because one is derived from a doublet P 1 half and the other is divided by a doublet S 1 half term. And there's a very small splitting here, now we're down to 5/100ths of an inverse centimeter, but it's there and it had to be explained. And it's explained by QED. It's very interesting what goes on here. What QED found is that radiative relaxation, right? So fluorescence or phosphorescence, the spontaneous emission out of these levels back to the ground state, that's caused by the interaction of these excited states with fluctuations in the vacuum field that fills all space. These two levels couple differently to the ground state, and therefore they have different lifetimes. If they have different lifetimes, then the energy time uncertainty relationship shifts those levels just ever so slightly and breaks the degeneracy between them. So it turns out this splitting is related to the structure of the universe. To finally get the whole answer, the one other thing that we haven't taken care of now is that the nucleus itself, the hydrogen nucleus, the proton, it has a nuclear spin, and that can couple to the spin of the electron as well. And so there's a hyperfine splitting that it comes about as well to get that last little bit in there. But we haven't been talking about nuclear spin effects here. Okay, so again, to summarize some of these consequences of the Dirac equation and QED on spectroscopy, right? The Dirac equation, it discovers spin a priori. It falls out naturally after we do a full relativistic treatment. It then explains the Pauli exclusion principle and justifies it as a consequence of this spin that came about from quantizing in 4 dimensions. It also introduces spin-orbit coupling because spin we can really understand as an intrinsic magnetic moment of the electron. It's another angular momentum, and angular momenta can couple. Here it couples. Spin-orbit coupling leads to shifts in levels, and it's going to become increasingly important as Z, the atomic number, increases. QED explains spontaneous emission in much greater detail. It shows how it's caused by the interaction of excited states with fluctuations in the vacuum field, that vacuum field that fills all space and its quantized field interacting with excited states, making them relax by jiggling them around, and then they relax. And the rate at which they relax is going to be related to the description of those in terms of their angular momenta.